All right, class, welcome to our physics lesson today. We are studying sound and interference. And I'm not sure at what point you're listening to this. You may have done a lot of the lab. You may haven't even started it yet. That's fine. With this one, we are introducing some new terms and things that you'll be using in the lab. So you may even be coming in here midstream. So anyways, let's dig into this. We did take a sneak peek at this stuff, some of this stuff anyways, at the very end of the lesson last time, but we're going to start here today with sound. Okay, so sound is a wave, and let me bring up my little animation so that we can deal with this. Oh, hold up, no, I want to turn on the pointer like I had the other day. Okay, so now when I mouse around on here, you can see the little dot. Okay, so check this out. Sound is a wave. What type of a wave is sound, right? You should have noticed in last time's lab, if you think about it, right? This is how sound works, right? You have all these little air particles, and if we track an individual particle, it's just moving back and forth and back and forth and back and forth, right? So it's moving this way, and the wave is also propagating that direction, right? Sound is a longitudinal wave. Specifically, it's a compression wave, right? You have this thing here that's moving back and forth, and it compresses the particle, and that compression, that energy, that's the thing that's traveling, right? It's this pressure. A lot of the times when they make graphs of sound, you look at, okay, how is the pressure changing? And you can see, right, here's an area, right? These are little areas where the pressure is much higher. And that's all sound is, right? It's the air molecules are a little bit more compact, and that energy that's compressing the sound, that's the thing that's moving. The individual bits of air are just moving back and forth, and back and forth, right? I mean, that's all that they're doing, okay? So how does any sound wave originate? With a vibration. Okay, here I've got some plate that's moving. This is kind of like an imitation of what a speaker does, right? See, anything that vibrates is going to produce sound. Sometimes we can hear the sound, sometimes we can't, right? Slap the wall. The sound that you hear is the vibration of the wall. When you play the guitar, right? You pluck a guitar string. It's the vibration of that string, right? Imagine that this is a guitar string, right? It's vibrating and it compresses the air around it, and then that compression wave travels out, and as you'll see in the little animation that you'll watch, in the lab, hit your eardrum and makes your eardrum vibrate, right? But it's all about vibrations, right? Sound is all about vibrations, and so here you can see a vibration, a longitudinal wave. You can see the compression travel, right? And we could go over all the features in here, but we kind of talked about all that stuff last time. So, moving on. All right, with wave interference. So this is important. We looked at this animation in last time's lab. So here's the first wave, and you notice, okay, this wave isn't moving. It's just kind of standing still here, and then underneath it you have a wave that's traveling, okay? And all this is trying to show you is what do things look like as the waves move and interact with each other, okay? So it's like I'm taking this wave here and I'm adding it to the wave underneath it. So let me find a good place to pause this. How about right here? Okay, check this out. So I'm taking this wave here, and I'm adding this wave to it. So if you were to think about, if you were to look at their amplitudes, right, here's this amplitude, here's this amplitude. Look at this amplitude, okay? This amplitude here is this plus this, okay? And it gives me this thing that has twice the amplitude. Same thing down here. If I were to keep going, here's the amplitude, here's the amplitude. You can see that that's double, right? I'm taking these two waves, I'm adding them together, and I get this superposition of the two waves. Superposition! That's kind of fun to say. But that's all we're doing is we add the two waves directly. And so one of the really cool things is that if you let this run, so let me find a different place to pause this. Okay, check this out, right? Now, when we add the two waves together, okay, so here's the little middle line, here's this, here's the middle line. Now notice that this is down, so I've got a positive amplitude, a negative amplitude. When I add those together, what do I get? Well, something that's basically zero, right? Right now, these two waves are completely out, we call this, they're out of phase. They're completely out of phase, so they add to zero, okay? So you get nothing. So this is called destructive interference. The one that we looked at before is constructive interference, right? When the waves add together to make a huge wave, constructive interference. But in this case, right now, when they're out of phase and they're adding together to cancel, that's destructive interference, right? And so we're going to look at standing waves here in just a second, but this is how all waves add together. And anything that is a wave is going to do this. Okay, so sound, light, all the different types of waves you can get to add together, right? You can pump sound into a room. So how do you think noise-canceling headphones work, right? You have one sound wave coming in from the outside, and so the speakers generate a sound wave that's completely out of phase with that to cancel it, to give you no sound, right? That's how those noise-canceling headphones work, is they're playing a sound that's out of phase to the sound that is around you to cancel it out so that you hear nothing. There's actually a lot of sound going on in technology like that. So this happens all the time. In class, we would have done an experiment with light where you would have been able to see light interfering with itself to get bright and dark spots. We'll see. I'm going to try and find a video for that for next time's lab. Anyways, so let's keep going, right? This is wave interference. Right now it's constructive. Now they're getting out of phase. They're totally out of phase. That was total destructive interference, right? But you can be anywhere in between where the waves add together in funny different waves to give you all kinds of different things. Okay. So let's talk about this for a second. So a standing wave. Actually, let's hop out. Let's see here. Can I... Okay, technology, come on. No, I just want a board. I just want a whiteboard. Look, there's a... Hold up. Whatever, I'm just going to write on this space. There's a way that I can get a whiteboard in here, but I can't remember how to do it. Okay, so let's pretend that we have some string, okay? And on, and this end of the string is tied off to a wall. And so over here, and you would have seen this in last time's lab, right? Let's say that you're holding on to this side, that's your hand. And look, here you are. And we're going to take this and we're going to flick this thing, right? And so if we were to flick it, you'd get this little bump in here. And the bump would travel forward, right? The bump's going forward, the bump's going forward, it's going forward. Okay, now when we get to this wall, let's say if this is tied securely to the wall, so it's a fixed end, you should know from last time's lab that this is going to reflect back, but it reflects back, and I'm going to draw the reflection in green. It reflects back underneath on the opposite side. So the wave would keep going this way, right? Keep going this way until it got back to your hand. And one of the things that you were supposed to experiment with in last time's lab is, so when the green wave, when the reflection is coming back, well, what happens when you send a wave forward? So you've got a red one going forward, a green one going back. Well, when they run into each other, you're going to get examples of constructive and destructive interference, okay? And then the question is, well, what if you did this continually? What if you kept sending red waves and then green waves kept coming back, right? What would the situation look like then? Okay? And In today's lab, you're going to see that in one of the videos I show. You'll see me with a drill and a string, and the drill is continuously making waves that travel down the string, reflect off of the other side, a thing my friend is holding, and then interfere, and you get these weird, crazy patterns. And so what we're going to look at in these animations here are what those weird, crazy patterns are and how they work, okay? So let's take a look at that. So over here, this is the first pattern you can get, and you would have seen this in the video. And so this is what we call a standing wave, okay? And class, all a standing wave is you have the incoming waves coming this way, the reflected waves going this way. They're interfering with each other in all kinds of crazy ways as they travel along the line, and it makes this pattern that we call a standing wave. And here in the middle, you've got a place where you have a lot of constructive interference, right? Because you're getting maximum amplitudes here, okay? And then on the ends where it's kind of held here in place and it's held here in place over here, so technically those are destructive interference. We call the motionless places nodes, and the middle places where there's a lot of motion, that's called an antinode. But this is the first pattern you can get. This is sometimes called when you're dealing with sound, it's called the first harmonic, right? Because it's the most basic shape that you can get. And now looking at this, if this was a string, how much of a wavelength are we looking at? I give you, if you think about this, well, what's the shape of a normal wave? Well, it goes up and down. Oh, look. Oh, oops. It goes up and down. This is only half of a wavelength, okay? So the first harmonic, which has one antinode, is only half of a wavelength, okay? If I change the frequency, right, if I change the rate that I send waves down the system, well, then I can get something different. So same string, new frequency, and I get a different pattern, okay? Check this one out. Here, okay, so I'm going to freeze this animation for a second so I can draw on here a little bit. Orange. Okay, so in here, I've got two antinodes, all right? Two antinodes, and right, these are places of constructive interference where you're going to get maximum amplitude. And then I've got 1, 2, 3 nodes, right? And those are places where the string isn't doing anything. And you'll see this on the video that I play. And so here's a place right in the middle of the string where you have complete destructive interference. The string can't go anywhere. It's not moving up, it's not moving down here, it's just totally still. Well, not totally still, but almost completely still. Because you have a lot of destructive interference happening in this place, whereas over here on the antinodes you have a lot of constructive interference. So this would be the first harmonic. This here is the second harmonic. And all musical instruments, by the way, are based off of this principle that you can get different harmonics. And okay, so the other thing to show here is, hold up, I can wipe, yeah, clear. I can clear all the strokes. Check this out. So we talked a little bit already about like how much of a wave we're seeing. So this is 1/2 of a wavelength. But here, you get the whole thing, right? Here's the up part, here's the down, right? This is one complete wavelength. So this is the first harmonic, this is the second harmonic. So at the first harmonic I only have half a wavelength. At the second harmonic I have a complete wavelength. Well, what do you think the third harmonic's going to be like? How many wavelengths am I going to have? Let you think about it. Hopefully you're making a guess. And if you guessed, well, this is 1/2. Here's 2 halves. Well, I'm going to have 3 halves here. or 1.5, right? Then you're thinking along the correct lines if that's the case. So here's the third harmonic. I have 3 antinodes, and then I have 1, 2, 3, 4 nodes. But if you look at the number of wavelengths, I have 1.5 wavelengths there in my standing wave. Okay? So all of these are standing waves, same string. Just I'm sending different frequencies down, and the different frequencies give me different wavelengths. Okay? And when you watch the videos, one of the things you're going to be looking at and thinking about is how does the wavelength change as the frequency increases. So for example, this has a really long wavelength. This one, the wavelength is the length of the string. Here, look, the wavelength is only 2/3 of the string, right? So my wavelength keeps getting smaller and smaller, and if I kept going down, it'd get smaller and smaller still. And then think about what's happening to the frequency as the wavelength gets smaller. And you're going to see that in all of the different demonstrations we do in today's labs. Okay? So, these are waves on a string. These are standing waves, and different harmonics. Okay? Oh, and by the way, right, these are really good illustrations of what standing waves look like in a transverse space. So, but what would all this look like in a longitudinal space? In what sound is actually doing? Well, that's what this animation is for. So here up top, you can see a column of air, and you can see what's happening to the pressure. So this is the pressure, and you can see how the pressure is changing. But this is what a standing wave would look like longitudinally, where you can see the compression is moving back and forth, but you do have that rhythmic pattern, and then you can see the pattern again down here in this space. But this is what it would look like in a column of air. So for example, up here, this is what standing waves look like on a guitar string or piano strings, right? But this is what it looks like if you're playing the flute or any instrument that is built off of that is based off of vibrating a column of air, right? A flute is a good example of this. Trombone, right? Any of the brass instruments are just pipe organs, right? This is a perfect example of what a pipe organ is doing. How the air column vibrates within a pipe organ to produce the different sounds that we hear, okay? But these are standing waves in a pipe column of air. And then, last but not least, right, this looks a little crazy, but this is just a little sneak peek at what we're looking at next time, right? Sound is a wave, but so is light somehow, right? And that's what the topic for next time is going to be. Is we're going to look at, well, how is light a wave? Okay, well, just to kind of give you a little taste of what's going on, this is an antenna. Well, it's a funny looking antenna. But imagine you have electrons that are zipping up and zipping down and zipping up and zipping down, right? So I have electrons that are, and again, waves are all about vibrations, right? I've got an electron that's vibrating back and forth. And so think about this. As this electron goes zipping around in here, back and forth, any moving electrons, we already know that they produce magnetic fields. And an electron by itself produces an electric field. So if I have a moving electron, something that's accelerating, right? It's accelerating because it's having to turn around and go back and forth and back and forth. It produces an electric and a magnetic field. Well, that's all light is. It's an electromagnetic wave. So accelerated electrons produce electromagnetic waves, which are light. And so this is an example of what a radio looks like. And you've got these radio waves pumping off of this antenna where the electrons are accelerating back and forth. And again, we'll talk a lot more about this next time, but just as a sneak peek to kind of tie all of our topics together. That's what's going on. Good luck with today's material. Again, if you guys have any questions, leave them in the comments or send us emails, right? Talk to us about what's going on. Hope you're all doing well, and good luck with today's stuff. Thanks.